This video provides a detailed explanation of the sequence editor function of the Signal Quality Analyzer-R MP1900A, designed to maximize the debugging and validation capabilities for PCIe 6.0 and USB. First, we will provide a detailed explanation of the technical issues that need to be overcome. Next, we will overview the sequence editor function, which gives us an effective means of solving these issues. Finally, we will deepen your understanding by looking at some specific verification examples. Watching this video through to the end should help you be more proficient with the sequence editor function. In recent years, advances in AI technologies have led to a dramatic increase in the volume of data being handled by data centers and servers. As a result, the signal integrity of high-speed digital interfaces has become extremely important. For high-speed standards such as PCIe and USB, the key factors affecting stable communication include transmission line design, noise countermeasures, and compliance testing. Engineers need to consider these factors from the earliest stages of the design process. Typically, compliance testing for digital interface standards involves only a limited set of test combinations. These tests primarily focus on verifying normal operation, but often fail to adequately address how the interface behaves under abnormal conditions or performs under stress. As a result, the scope of the testing may not cover all the scenarios necessary to ensure robust system reliability. If a product is shipped after having undergone such limited testing, there is a risk of issues arising in real-world applications. Once the product is integrated into a system, identifying the root cause of any malfunction becomes extremely difficult. Unfortunately, the comprehensive verification of an interface's behavior under abnormal or high-load conditions requires an enormous number of test combinations. Traditional manual or distributed testing approaches can't cover all these scenarios. Therefore, there is an urgent need for a validation solution that strikes a balance between efficiency and reliability. In response to this need, Anritsu's sequence editor function provides comprehensive support for everything, from constructing test patterns and sequences for high-speed digital interface verification testing to automating tests, offering a solution that is both efficient and reliable. Sequence Editor is a feature of the high-performance BERT, Signal Quality Analyzer-R MP1900A. It supports a wide range of standards for each generation, including PCIe 6.0 and USB 3.1 Gen 2. By combining the sequence editor and the MP1900A with a protocol analyzer or an oscilloscope, more advanced verification becomes possible. For example, our partner company Teledyne LaCroix's protocol analyzer, the Summit M616, is designed for PCIe 6.0 design and testing, and its extensive analysis capabilities enable detailed protocol analysis. Similarly, Teledyne LaCroix's high-bandwidth oscilloscope Wavemaster 8000 HD is equipped with advanced serial data analysis features, including eye diagrams, jitter analysis, and noise analysis, enabling outstanding signal characterization and debugging at every stage of product development. The sequence editor is equipped with an intuitive GUI through which users can easily construct test sequences for abnormal conditions and stress testing. Even when we are working with a large number of sequences, it enables efficient creation and management. The sequence editor can flexibly accommodate not only the normal operation of PCIe, USB-compatible devices, but also abnormal link state transition testing and stress testing. This enables flexible testing in compliance with all requirements, as well as the verification of physical layer performance, the reproduction of logical layer malfunction behaviors, and efficient root cause analysis. Furthermore, the sequence editor supports multi-channel evaluation, allowing us to simultaneously test multiple lanes and perform tests that simulate real-world environments. As a result, potential issues can be identified and resolved at an early stage, contributing to greater efficiency in the design and evaluation process as well as improved product quality. Let me explain the sequence editor feature in detail. Conducting a comprehensive physical layer test for PCIe and USB requires more than running the default link training sequence. Instead, the test plan should cover all the state transitions defined by the standard as well as scenarios involving abnormal behavior. Therefore, verifying the full range of state transitions of the link training and status state machine, LTSSM, as well as multiple test case behaviors, is required to ensure a thorough evaluation. Considering all the defined state transitions and abnormal scenarios provides a much broader validation of the system's behavior. To address the issues affecting these verifications, Anritsu offers the sequence editor function, which can be used in combination with the PAM4 PPG-MU196020A and SAP PPG-MU195020A modules that are compatible with the Signal Quality Analyzer-R MP1900A. The sequence editor offers an intuitive interface for creating custom patterns and sequences, supporting applications such as PCIe 1.6 and USB 3.2, making operation easy for anyone. Furthermore, combining this feature with the high-speed serial bus data analysis functions of the PAM4 EDMU196040B and SAEDMU195040A makes even faster and more efficient data analysis possible. The GUI of the sequence editor is shown here. The sequence editor's GUI provides per-block settings to allow sequence customization tailored to the USB and PCIe standards, such as SKP, EIOS, SyncOS insertion, precoding, and gray coding. Other configurable settings include TX preset settings and Scrambler LFSR selection for lanes other than lane 0. In the PCIe GUI, each sequence block can be configured as an electrical idle, a pattern with PCIe encoding, or an idle flit. The transmission duration for each block can be specified either numerically or in terms of a duration. The sequence itself can be edited by adding, copying, or deleting blocks. Each block can be edited at the bit level using the pattern editor, which greatly helps with the creation of test cases. The sequence editor features a break function, enabling the current block to be continuously output until a manual operation or an external AUX trigger is received. Engineers can use a cable to connect the protocol analyzer's trigger out to the PAM4 PPG AUX and of the MP1900A, allowing the MP1900A and the protocol analyzer to work together. When a trigger condition is detected, the protocol analyzer can send a signal to the MP1900A. When the protocol analyzer captures data and detects a 128B130B TS1, it immediately sends a trigger signal. Upon receiving this trigger, the MP1900A advances the sequence from the recovery equalization phase 1 TS1 to the recovery receiver lock TS1 pattern. Furthermore, during the transmission of a specific block, the MP1900A can also output a trigger signal to a protocol analyzer or oscilloscope. The sequence editor also supports multi-channel configurations of up to 4 channels, so that multiple PCIe device lanes can be tested simultaneously. This allows for testing under conditions that closely resemble real-world usage environments. The MP1900A's multi-channel calibration function ensures that the data being output from every channel is synchronized. To address the complexity and high data rates of PCIe, it is critical to evaluate the receiver performance of the DUT, using not only the modified compliance patterns but also the training sets intended for link training. By leveraging the HSSB data analysis function, engineers can measure the bit error rate when training sets are used as the data source for loopback testing. Let's take a look at 4 practical examples of verification where the sequence editor can assist in debugging. The first example highlights the advantage of using the sequence editor. It allows you to extend the transmission period beyond the timeout defined by the specification. This makes it possible to keep the data flow to the DUT steady. As a result, you have more time to reliably debug the DUT operation. In this case, a timeout occurred during phase 1 of the 32G recovery equalization, and link training failed. Possible causes include logical errors or the DUT having an insufficient stress tolerance. By extending the timeout with the sequence editor, you can better address these issues. Here is another example of practical verification. By using the pattern editor function, engineers can modify the training set bits and guide the DUT toward alternative or custom LTSSM transitions. This allows engineers to modify the transition instructions from BERT as needed, and not be limited to loopback. As a result, the system offers greater flexibility. In this example, asserting the disable link bit causes the DUT to enter the LTSSM disabled state. This is accomplished during setup by configuring symbol 5, bit 1 in the 8B10BTS1 ordered set. This is an example of how the MP1900A transmits a TS1 ordered set with the disable link bit asserted. The DUT responds by returning the corresponding bit and then transitions to the LTSSM disabled state as expected. The third verification example demonstrates the 32G precoding function and the flexibility with which test cases can be created. This allows the BERT to transmit data bits that do not comply with the PCIe standards. These are abnormal data bits. By receiving this abnormal data, the DUT's response can be debugged. During link training, the MP1900A encounters a timeout at phase 1 of the 32G recovery equalization. This raises questions about whether the DUT fully decodes the 32G data or if an issue exists with LTSSM implementation on the DUT side. When analyzing such cases, engineers need to isolate the root cause of a bug. The status of the DUT's transmitter precoding request bit is monitored using both the MX18300A LTSSM log and the DUT's internal status register. In this scenario, the values do not match, which suggests a potential issue with the DUT's precoding process. For additional debugging, engineers may consider sending custom data patterns to the DUT. This involves toggling the precoding function and adjusting the transmitter precoding on bit, specifically symbol 7, bit 6, within TS1 ordered sets. By introducing these stimuli, engineers can observe the DUT's response and identify the origin of the problem. For example, we can create a sequence where the transmitter precoding on bit is set to 0 while precoding is enabled. Using a protocol analyzer, engineers can enable precoding, set the data capture trigger, and perform verification. In the data captured after precoding, engineers can confirm that the transmitter precoding on bit is set to 0. Flexible test cases like this can be easily designed using the sequence editor. This is the fourth example of verification. By utilizing the jitter and noise modules of the MP1900A, engineers can inject jitter and noise into the device under test to perform stress testing. By incorporating a sequence editor that allows for control over the number of transmissions, we can evaluate the DUT's tolerance and receiver performance margin. In this case, the number of TS1 packet transmissions for loopback entry is limited to 10 sets, enabling engineers to examine how stress affects the DUT's reception performance. When the DUT is transitioned into loopback mode without any stress applied, it is confirmed that the loopback operation proceeds smoothly. Upon receiving the loopback entry sequence, that is, the TS1 sequence set, the DUT initiates loopback behavior in response to the modified compliance pattern transmitted from the MP1900A. Next, the same procedure is performed with added noise and jitter stress. As a result, the error rate in the modified compliance pattern is found to be approximately 3E4, indicating that the DUT failed to loop back data correctly. Log data captured by the protocol analyzer reveals that the DUT stopped operating midway through the loopback entry. This suggests that the impact of noise and jitter is significant, enough to prevent the DUT from reliably recognizing the 10 TS1 sequence sets created using the sequence editor. Another way of evaluating whether the DUT is halted in a specific state is to utilize the PCIe data analysis function of the MP1900A. However, it works with the PAM4 PPG sequence editor. It measures the BER of PCIe data from the DUT. For PCIe 6, it is also possible to set the loopback data to NOP FLIT. Furthermore, we can assess the FEC performance of the DUT by utilizing the FEC error insertion, analysis, and capture functions of the MP1900A. The sequence editor can transmit FEC patterns. Therefore, we can create test cases for FEC error insertion and analysis. As we have seen in this video, the sequence editor enables detailed and flexible testing and debugging for PCIe and USB interfaces. Anritsu will continue to enhance its features to keep pace with the evolution of high-speed digital interface technologies. By supporting signal quality assurance and improving design efficiency, we consistently deliver significant value to your development processes.